Alright, welcome to this video where we're going to look at solving equations using opposite operations. So let's remember that we've already looked at what it means to solve an equation. First of all, an equation is like a balance. Both sides of the equation are equal, they're the same. And to solve an equation means to figure out what the letter is equal to. So we want to know, what does the variable x have to be in order for this equation to be balanced? Because remember, a variable can be anything. It could be 2, it could be a million, it could be -5. But in the case of an equation, there's always one number that makes the equation true. In this case, what plus 5 equals 7? Well, x has to be equal to 2. And x couldn't be 4 in this case, because then the equation wouldn't be balanced. X has to be 2. And we solve that just by looking at the equation, by inspection. But sometimes you can't look at an equation and know easily what the variable is. For example, this one, 3x minus 7 divided by 2 equals 4. It's very hard to look at this and realize that x is 5. In the case of these equations, solving by inspection is hard, and we need another way to solve equations. And the way we do that is by using something called opposite operations. Okay, before we talk exactly about using opposite operations, we need to understand what our goal is when we're solving an equation using opposite operations. Anytime you're solving an equation, remember, our goal is to know what x is equal to. For example, in x minus 3 equals 10, our goal is to know that x equals 13. This is called isolating the variable. Notice in our final solution, our final answer, there's no numbers on the side with the x. Here we had a -3 with the x. At the end we want x to be alone and the numbers to be on the other side. That's called isolating the variable or getting it alone. And that's our goal when we solve equations. Right. Our first major idea that's going to help us in solving equations is that every operation has an opposite operation. So plus and minus are opposite operations. Multiplication and division are opposite operations, and square and square rooting are opposite operations. Even operations such as cubing has the cubed root, and putting to the exponent 5 is something called the fifth root. So every operation in math has an opposite operation. What I mean by that is that opposite operation undoes it. So let's start with a number. I'm going to use my favorite number, 7. And let's add something to it. Let's add 3. By adding 3, I've changed this number. 7 plus 3 is now 10. But if I added 3 and then subtracted 3, I'm still at 7. 10 minus 3 is 7. Because adding 3 and subtracting 3 are opposites. They undo each other. It's like we did nothing at all. Same thing if I multiplied. So let's start with 7 and multiply it by 3. That would change our value to 21. But if I then divided by 3, 21 divided by 3 is right back to 7 where we started, and it equals 7. Because multiplying and dividing are opposites, so if I multiply and divide by the exact same number, it's like I did nothing at all. And let's square 7, and then take the square root. So that would be the square root of 49, which is 7. Again, we're right back where we started, because squaring and square rooting are the opposites. So if we use opposite operations, we get right back to where we started. Our second idea that we're going to use is this. Whatever you do to one side of the equation, you must do to another side of the equation. So remember, equations are like balances. Let's pick an equation, 5 equals 5. Right now, this equation is balanced because both these sides are equal. Let's say we wanted to change this side of our equation. 7 is my favorite number, so let's say I wanted to add 2 to make it 7. Now our equation says 7 equals 5, and we are out of balance, because 7 doesn't equal 5. So we can't do that. But if we also do it to the other side of the equation, we're still in balance. 7 still equals 7. So if you add something to one side of your equation, you become out of balance. But if you do the same thing to the other side of the equation, you're still in balance, and it's still an equation. Alright, so now the question becomes, how can we use our two ideas to accomplish our goal of isolating the variable? So here's 4 examples that we're going to look at, and the question asks us to solve each of them. Now since these are one-step equations, there's only one number on each side with the variable. We could solve these by inspection. Let's do that now, just so we have an idea of what the answers are when we do it by opposite operations. So what plus 7 equals 12? Well, we know that should be 5. So when we solve it by opposite operations, we'll have a way of checking our answer. What minus 4 is 3? Well, b would be 7 in this case, because 7 minus 4 is 3. What divided by 4 equals 3? Well, 12 divided by 4 is 3, so you know n is 12. 3 times what equals 18? 6. So the f would have to be 6 in this case. So we know what all the answers are, but we're going to do it by opposite operations, just so we can get the hang of how we use these ideas to accomplish our goal. So let's start over here at x plus 7 equals 12. Now remember, our goal was to isolate the variable. Our goal is to get x alone. But on this side with the x, we have this plus 7. We don't want it there because we want x to be isolated. So we use key idea number 1. Every operation has an opposite operation. So what's the opposite of adding and 7? Well, that would be subtracting 7. So I know that if I subtract 7 from this side, these two things will cancel out because adding 7 and subtracting 7 are opposites, and the only thing that's left is this x. But we also have to remember idea number 2. We can't just subtract 7 from this side, we also have to subtract it from the other side. So on the left side of the equation, those canceled out, and we're just left with x. And on the right side of our equation, 12 minus 7 is 5. So we get x equals 5, which if you remember when we did it by inspection, we said 5 plus 7 equals 12. So we get the same answer by doing it using these two ideas, which is called opposite operations. Let's try another one. b minus 4 equals 3. So remember, our goal is to isolate the variable, get it alone, but it has this minus 4 on the side with the b. Idea number 1 says every operation has an opposite. The opposite of subtracting 4 is adding 4, but I have to do it to both sides of the equation. So I also do it to my other side of the equation so we can stay in balance. Now, on our left side, minus 4 plus 4 cancels out. That's the reason we added 4. We could have added anything we wanted. We chose to add 4 because we knew minus 4 plus 4 is 0, and the only thing that's left is b. And on this side, 3 plus 4 is 7. And we knew that was going to be the answer. We knew 7 minus 4 was 3. And we got that using opposite operations. We can do the same thing when we divide and when we multiply. The opposite of dividing by 4 is multiplying by 4. But I do it to both sides of the equation to be fair, to keep it in balance. Dividing by 4 and multiplying by 4, they cancel out, right? Times 4 divided by 4, that's like 1, and anything times 1 is itself. So those are gone, and the only thing that's left is n. While on the right side of our equation, 3 times 4 is 12. So we're left with n equals 12. And we already said 12 divided by 4 was 3. So we know we got the right answer. Finally, 3, and remember that's times f, equals 18. The opposite of multiplying f by 3 would be dividing it by 3. But I do it to both sides of our equation to keep it in balance. Those cancel out, because times 3 and divided by 3 is just 1, and 1f is just f. So f equals 18 divided by 3 is 6. And we already said 3 times 6 was 18, so we know we got the correct answer. So that's how we use idea number 1 and idea number 2 to accomplish our goal of isolating the variable and solving equations.